In this video, we will introduce the concept of maximum and minimum values. So to begin, let me just define and then graphically illustrate these two concepts. So if we have some function f, and we denote the domain of f by s. So to get a graph of a function in here, let's suppose that our domain is some interval, and the function graphically looks something like this. So let's say this is y equals f of x. We say that f of c is the maximum value of the function f on the domain if the value f of c is bigger than or equal to f of x for all other x values in the set S. So in this case, we see that we have this point on our graph corresponding to, maybe let's call it an input C1. If we trace over to the y-axis, we have our output f of C1. And regardless of the input that we plug in, f of C1 is the largest possible output, which we can see graphically. So we would refer to f of C1 as the maximum value. Likewise, we say that f of c is the minimum value of f on the domain if the function value at c is less than or equal to every other function value in that domain. And looking at our graph, we see this second point corresponding to maybe an input we will call C2. And if we trace over to the y-axis, we have f of C2. And of all possible inputs that we can plug in from our function, this graphically we see is the absolute smallest output, or the smallest output that we can have. So this would correspond to f of c2 being the minimum value of our function. We would say that the maximum is attained at the point c1, the minimum is attained at the point c2, but it's the function output that we call the max value and the min value. Now, a natural question to ask is, when does a function f have a maximum or a minimum value? So to kind of introduce this idea, let me go ahead and just graph a function. I'm going to graph y equals 1 over x, and I'm going to specifically consider it on the domain 0 to infinity. And if we look at the graph, we notice in this case the function will have no maximum or no minimum value. And at first this may not be the most intuitive concept. You might look at the graph and say, oh, well, the maximum value is infinity and the minimum value is 0. But the problem is you need to have inputs that correspond to those outputs. There is no input that will give us an output of infinity. That's not a number. And there is no input that will give us an output of 0. So in this case, we would say no maximum or minimum values. But there is a certain case where we can guarantee the existence of maximum and minimum values. This is something called the max-min property. If f is a continuous function on a closed interval, then f attains both a maximum value and a minimum value on the interval. And the key here is that there are two hypotheses. We need a continuous function, and we need to look specifically on a closed interval. So our previous example where we considered the function y equals 1 over x, we considered it on an interval that was not closed. It was on the open interval from 0 to infinity. So instead, let's consider what's going on from 1 to 2. So if we were to represent this graphically, so at 1 the output is 1, at 2 the output is 1/2, and y over 1 over x looks, roughly speaking, something like this. And we see that in this case that we do have an absolute maximum value. We would say that the max value occurs at 1. So the max value would be f of 1 equals 1. And we have a minimum value, a smallest output on this interval. It occurs at 2. So f of 2 equals 1/2. And the big question that one might now ask is, well, if we have a continuous function on a closed interval, where will the absolute max, or where will the maximum value and the minimum value occur? One possibility is illustrated in the graph above. It occurs possibly at one of the endpoints of the interval. But let me draw another arbitrary looking graph on a closed interval from a to b. So a continuous function could look, roughly speaking, something like this. So continuous function y equals f of x on the closed interval from a to b. The max-min property guarantees the existence of a maximum and minimum value, and from a graphical perspective we can see exactly where they occur. The maximum value and the minimum value. And the key observation here is to note that both of these points on the graph share a very common characteristic. The tangent line, where that maximum and the minimum occur, are both horizontal. That is to say, a slope of 0. So if we were to say C1 is where the maximum value occurs, note that f prime of C1 is equal to 0. If C2 is where the minimum value occurs, f prime of C2 equals 0. And for this reason, these are going to be points that we call critical points. So the question that we ask is, where does f attain a maximum or minimum value? And we said it turns out maybe at an endpoint of the interval or one of these special points inside the interval. So if c is a point in the domain of a function where that first derivative is equal to 0, something the text calls a stationary point, or if f prime of c is undefined, we call c a critical point of f. And something about this second type of point is very important to note. C has to be a point in the domain with f prime c undefined. So the typical critical point we are going to have is just where the first derivative is equal to 0, but occasionally we will have this second type of critical point as well. And in terms of restating that max-min property, a continuous function on a closed interval is going to attain both a maximum and minimum value on that interval, and then furthermore, from the observations that we've made just intuitively and graphically, the maximum and minimum values must occur at one of two types of points. A critical point inside the interval, and it has to be in the interval, or an endpoint of the interval, either A or B. And this gives us a very nice procedure we can use to determine the max or minimum values. We find the critical points of our function on the interval, we look at the endpoints, and we evaluate our function at each of these, and that's going to give us a list of numbers. From that list of numbers, we pick the largest value, that's the maximum. We pick the smallest value, that will be the minimum. So let's illustrate this with a few nice concrete examples. So a very typical example. Identify the critical points and find the maximum and minimum values of the given function on the closed interval. So let me go ahead and just note that the function that we are looking at is a polynomial, and all polynomial functions are continuous. And the interval that we have is closed. So the max-min property guarantees the existence of the maximum and minimum values. We are just going to go ahead and find them. So the first step is to find the critical points. And specifically, we need to find the critical points in our interval. So find all of the critical points in -1/2 to 2. So in order to find the critical points, we take our function and we differentiate it. So working term by term, f prime of x by the power rule is going to be -6x squared plus 6x. And what we would like to know in terms of the critical points is where is that first derivative equal to 0. And I put a question mark over the equal sign just to indicate I want to solve where this thing is equal to 0. So in order to find where a polynomial equation is equal to 0, we factor. I'm going to go ahead and pull a -6x out of each term. and that leaves me with an x and a minus 1 left over. So we will have two critical points, x equals 0, x equals 1. And notice both of these critical points, x equals 0 and x equals 1, are inside our interval. So the critical points, and I will abbreviate that with just CP, are x equals 0, x equals 1. Now the second step is to evaluate our function at the endpoints and the critical points to determine what is the maximum and minimum values. So our endpoints, minus 1/2 is 1. Then we have 0 as a critical point, 1 as a critical point, and 2 as an endpoint. So if I go ahead and just evaluate the function, f of minus 1/2 is 1, f of 0 is 0, f of 1 is 1, and f of 2 is minus 4. And looking at these numbers, 0, 1, and minus 4, we see that minus 4 is the smallest. So minus 4 is the minimum value. And the largest number that we have is 1. So we have a maximum value of 1, which occurs at minus 1/2 and occurs at 1. And if that maximum or minimum value occurs at more than one point, we should somehow indicate what those points are. So once again, from a procedural or big picture perspective, if we want to find these maximum and minimum values, it's a two-step process. Find the critical points of your function inside the interval, and then we evaluate our function at the critical points in the interval and the endpoints. That gives us a list of numbers, and from that list of numbers we pick the largest and the smallest values. Those are the maxes and minimums.